Welcome to today's lecture. Our lecture today will focus on classes of scalars and vectors known as eigenvalues and eigenvectors. And this has application in diverse fields such as computer graphics, mechanical vibrations, population dynamics, heat flow, quantum mechanics, and economics. And these are just a few to actually mention. So you may be wondering what eigenvalues and eigenvectors are. It says that if we have a square matrix of dimension n by n, so a square matrix of dimension n by n, then and a non-zero vector, which is v, or in some book mostly you see x. So this is our non-zero vector, and if this AV is a scalar multiple of V, then we can write this. So this actually, for some lambda, the lambda here is, so this lambda is the eigenvalue, which is our scalar. Then you have your V, which is your vector, your non-zero vector, and it's called the eigenvectors as well. So these are the properties you have to have in mind when you are talking about our eigenvalues. And in general, the image of the vector V under multiplication by a square matrix actually differs from V in both magnitude and direction. So you have AV points of the original line through the origin. So this is the ordinary vector that you have. And when I have lambda equal to 2, which is showing the direction, which is stretched to a double length of the same line, representing the eigenvector. So in finding our eigenvalues, what we call the characteristic equation is very important to look at. Already we have established that our A, V, is equal to lambda V as well. And we want to write the characteristic equation in this form. So if you want to, you can write AV minus, you have what, lambda V equal to 0. You can bring lambda out, right? So that you can bring our V out. So that I have A minus lambda V to be equal to 0 here. You realize that you have virtually two equations here. So you have V equal to 0, A minus lambda here equal to 0. And I can write this, which shows a non-trivial solution exists. I can write A minus the identity times lambda, you still get the same thing. So the identity, which is I lambda, to be equal to 0. And this solution only exists when A minus I lambda or lambda I is actually singular. And if it's singular, what it means is that from our previous lesson, then the determinant should be equal to what? 0. The determinant should be equal to 0. So this is the process from A minus lambda I. We subtract lambda from each diagonal of the entry of A. Then we expand, find the determinant. Then we solve for lambda, which are eigenvalues, and lambda And for each lambda, we are going to find its corresponding eigenvectors as well. Let's look at an eigenvector of a 2 by 2 matrix like we are talking about. So that if I have a vector, let's say I have a vector v, which is equal to uh, 1, 2, and this vector v, which is equal to 1, 2, is an eigenvector of the matrix A. So our matrix A has entries 3, 0, 8, -1. And a corresponding lambda, let's say we have a corresponding lambda which is equal to 3. What does this mean? This means that AS, our AX, equal to lambda x, or V, AV. So let's use V because that's what we have been using. So AV equal to my lambda V here means that I have AV. So this is the matrix A, 3, 0, 8, -1 times the vector 1, 2. If you find the matrix multiplication, this is going to give us 3, 6. And 3, 6, you have 3, 1, 2. So what do you notice? You notice that this is our V, right? With the scalar 3. So geometrically, multiplication by A has actually stretched the vector x by a factor of 3, which is what you have here. And it's very important if we want to compute our eigenvalues and our eigenvectors. So in the computation, like we expressed from here, we need to form this, then expand the determinants from there as well. So let's take an example here if we want to. So we have the matrix. This is the matrix that we have. So we would like to find the eigenvalues and the eigenvectors. So you need to form your A minus lambda I, and if you do so, it means that your new A will actually be equal to, let's take it slowly, will actually be equal to what you have. So it's a diagonal you are interested in. So 4 minus lambda. For the diagonal entry, you have 1, you have 2, then 3 minus lambda. Okay, so the next thing to do is find the determinant. And you know what the determinant is. The determinant of this matrix is going to be this and that, right? So I find the determinants. So you have the determinant A minus lambda with I, right? So you have this and that as well. So I have 4 minus lambda 3 minus lambda minus 1. So this times this minus this times that. We already have a fair idea or a previous knowledge on how to find the determinants of matrix already. So you multiply your leading diagonals, then you subtract the off diagonals, the product of the off diagonals as well. So if you do that, then this is what you have. The expression you have will be this. Simplify, and this is what we have left. Now, you need to find the values for the lambda. So you can express this in terms of what? That as well. And your eigenvalues are going to give you lambda 1 to be 5 and lambda 2 to be equal to what? 2 as well. For each eigenvalue, we need to find its corresponding vectors as well. So the initial matrix we had, which is A equal to, it was 4 minus what? Lambda. You had 1, 2, then 3 minus lambda as well. Okay. So we come back, you substitute for each lambda, you substitute. So you realize that if I substitute lambda equal to 5, then my new A becomes, so 5 minus 1 here. Then you have 1, you have 2, 3 minus 5 is going to give us negative 2. Okay. So this is what you have. So you have A minus lambda to be equal to this. So then from this matrix, so looking at it from here, so it's just our initial A minus lambda, which is equal to this. And this is the initial formula that we had. So for each lambda, this is what we saw. A minus lambda IV equal to 0. Like when we started from here as well. So for each lambda, you want to find your A minus lambda I, this lambda I here, V equal to what? 0. So that is the substitution you actually do from here. So you want to write A minus lambda I V equal to 0. So your interest now is finding the values of this actually. So what do you have? So you have your matrix. So you have minus 1, 2, 1, negative 2. Then you want to find x, y to be equal to 0. Okay, and we are already familiar with this, finding the values of x and y already. So if you do this, this is the eigenvector v1 for its corresponding eigenvalue lambda 5. And you do the same, you go through the same process to find for when lambda is equal to 2 as well. So for when lambda is equal to 2, we have A. So you have 4 minus lambda, which is 2. then we have 1, we have 2, then 3 minus 2. Okay, so this is what we have. So this is going to give us 2 1 2 1. Okay, so this is what you are solving. So you are solving this 2 2 1 1. So find x y equal to 0 as well, and this will give you the eigenvector 2 for its corresponding eigenvalue as well. So when this happens, what it actually means is that the character always, so let's make a note. We want to make a note here, and so making a note. Okay, so what it means is that when the determinant is always expanded, it takes the characteristic equation of the form lambda, so lambda to the power n plus c1 lambda to the power n minus 1 plus 2, the term where you have plus cn equal to 0, where the left side of the equation is the polynomial degree of n, in which the coefficients of the lambda to the power n is equal to 1 as well. And this is what we are calling the characteristic equation. So that when you are given a matrix and you are asked to find the characteristic equation, it should be easier to actually go through as well. So we'll take, so what we did earlier was an example for a 2 by 2 matrix, and let's take an example of a 3 by 3 matrix as well. If I'm given a matrix, this B to be equal to this, and I want to find the eigenvalues of the matrix, what I need to do is actually write the characteristic polynomial of A. So we can write a characteristic polynomial to be equal to this. So if you notice for this matrix, because column 1 has only 1 on 0 entry, we can actually expand it along 8. You remember when we were trying to find a determinant, we're saying that sometimes look for a row or column that has the least non-zero entry, which is this one. So you can actually expand it along that line, so you know that you have, so you realize that we have this and that, so that if I expand it along that line, then what it means is I have 2 minus lambda here, then I'll be left with this block you have here, 3 4 4 9. So then I can find the determinant of this matrix as well. So you have 3 minus your lambda, so I have 3 minus lambda, you have 4, then 4, 9 minus lambda. Okay, so what we have done is to expand just this part out as well. Okay, so if you do that, you only solve the determinant for this block, then you multiply by your 2 minus what? Your lambda here. So if you do that, this is what you have. So then your full characteristic equation now is going to be 2 minus lambda, 1 minus lambda, 11 from the expression here equal to 0. So we have 3 eigenvalues. So for a 3 by 3 matrix, we have 3 eigenvalues, and which will also mean that for each eigenvalue, we will need to find its corresponding eigenvectors as well. So you go through the same process, and you find the eigenvalues as well. This is also an example where you want to find the eigenvector for lambda 2 by solving this equal to that. So you already know the definition. This is the initial definition. Your matrix minus the lambda I. So this is what you have. You go through the process, you find for each eigenvalue. So this one, the eigenvalue was given as 2. Your eigenvector was given as this. Kindly pause for now and take your time to go through this example. And if you have any question or response, you can put that in the comment section. A few key properties of eigenvalues that you have to take notes of. The first one is summation of the eigenvalues. That the summation of the eigenvalues is going to be equal to the trace of our matrix. Maybe we would like to look at the previous example we had. If you wanted to find the trace of this matrix, what was it going to be? It's going to be adding the words leading diagonals, which is 4 plus what? 3, which will give us 7. That is a trace of the matrix. And it says that if I add sum my eigenvalues, it should be equal to the trace of the matrix. So that is the first property, which is this. Then the second one says that if the product of my eigenvalues should be equal to the determinant of A as well. Let's go back and look at the example that we did. What would be the product? The product of our eigenvalues in the example that we did. The product is 5 times 2. It's equal to 10. What would be the determinant if we wanted to find the determinant? That is going to be this times that, which is 12 minus 2 times 1, which is equal to 2. So 12 minus 2 is going to give us 10. And this property also holds as well. Then it says triangular implies diagonal. So that for every triangular matrix, the eigenvalues are exactly its diagonal entries as well. You can actually take your time, pause and verify all these properties as well, and leave your comments in the section as well. When we started, I did mention where eigenvalues actually show up too. A few takeaways you might want to think about is we are saying that a matrix times V, which is the scalar multiple of the vector, it's equal to lambda v, where our lambda is the eigenvalue and v, which is non-zero, is the eigenvector. If I want to find the eigenvalues and eigenvectors, I need to first write what the characteristic was equation, which is equal to this for lambda. Then for each corresponding lambda, I could find the eigenvectors using this as well. And we also mentioned that trace gives the sum of the eigenvalues. Determinant also gives their product as well. Then eigenanalysis actually has application in principal component analysis, vibration analysis, search ranking, and stability theory. Thank you so much for your time. Don't forget to subscribe as well.